We've talked to some of the members of the Frontier Fields team before, so you know what the project is. We've already introduced it a little bit, but let's give a review. With me here is Dr. Jennifer Lotz. She is the principal investigator for the Frontier Fields project survey. Jennifer, why don't you tell us a little bit about what Frontier Fields is and what you're hoping to accomplish?
Sure. So the Frontier Fields is an ambitious 3-year campaign to try to peer deeper into the universe than we have ever before. So you may have heard of the ultra deep field, right?
Yes.
So,
Oh, yes.
I don't know, about a year and a half ago, the director of the Hubble Space Telescope asked a group of scientists whether it was possible to top the ultra deep field. Right.
That's a tall order.
Yes, it is.
That's a very
because
tall
we've
order, yeah.
spent hundreds and hundreds of hours looking at one little patch of the sky, and we've learned a tremendous amount from that field. But we wanted to know, was there more to learn with Hubble about the early universe in the years between now and the launch of DUST? And so this group of astronomers said yes, but you got to use a trick, and that trick is employing Einstein's theory of general relativity to use something called gravitational lensing. So the most massive objects in the universe actually bend space and time around. So those most massive objects are clusters of galaxies. And this bending of space actually means that light traveling by the cluster gets bent, much in the way that light moving through a telescope gets bent. And so gravitational lensing means that the galaxies that are behind the cluster appear magnified, they're stretched out, they're brighter, they look bigger than they would otherwise. So these clusters are acting like natural telescopes.
So galaxies that would otherwise be out of Hubble's detection range come into Hubble's capabilities.
Exactly. So we've got our natural telescope and then Hubble. So it's kind of like two telescopes.
Yeah, it's like
right?
putting two pair of binoculars right up.
So I was actually going to say, I love this. I love this Frontier Fields because basically you're told you have a telescope, you take it to its limits,
yes,
and you reach the limits,
Yep.
and you're told you cannot go past this. It was like, whatever, we can use nature, to help us really to go further than we ever been. Using gravitational lensing. To me, that's extremely innovative, mind-boggling. It's amazing, and the images that are online live that are behind us are tremendous.
Yeah.
Absolutely tremendous.
So nobody knew. I mean, we had the deep field, we had the ultra deep field. Those were in two different areas of the sky, right?
Yes.
So we had two data points of what the sky looked like if you stared at it for a really long time, and now Frontier Fields, using this gravitational lensing technique to see even fainter back, is going to see how many other places of the sky?
Well, we're pointing at 6 clusters.
6 different clusters.
Yes, and we're also going to get fields that are similar to the ultra deep field. So we're going to do this trick where we turn on 2 cameras at once with Hubble. So we've got one camera pointed at the cluster and another camera pointed a little bit away from the cluster. We're going to stare for a really long time at the cluster, so we might as well take your fields, which are these lensed lensed galaxies behind clusters. And then we have 6 new, almost ultra deep fields. So 12.
So you get the clusters, you get the lensing there in that, and this other parallel field is not going to necessarily be lensed, right?
Exactly.
It's just going to be an area of the sky, and you're looking at it because you can. Why not?
Yeah. Well, the ultra deep field is great, but it's one field, and we want to know whether the galaxies we see in that field are typical. And so if you look at more places in the sky, you get a better sense of.
So I guess another question Frontier Field will address was the Hubble deep field and ultra deep field, were they common? Are they common in the universe? Are we looking at a patch of the sky that is we're particularly lucky because we found this, or not lucky? This universe look like this everywhere,
right?
And that's actually a very important thing to do because it was very costly to do that.
I know, but I hear people say that, and I know what you're saying. I know you want to answer the question definitively, but come on, that seems kind of common sense to me. I mean, isn't it going to be pretty much the same everywhere you look? I mean, you're going to see galaxies.
Not necessarily.
Not necessarily, right?
So,
it's not so common sense.
No,
okay.
because the galaxies, we're pushing Hubble to the limits, right?
That's with the lensing. That's
with the lensing, but also the ultra deep field, right? So the things that we're seeing at the edge of our ability, right, near the edge of the beginning of the universe, the first billion or half a billion years of the universe. The things that we can detect with the ultra deep field are just the brightest things at that time, right? So they're kind of they're the big galaxies that will end up in clusters of galaxies later, right? And so they're fairly rare. right? So anything that we've detected at the earliest, the deepest images at the earliest times is going to be a rare galaxy.
Right. But I mean, sometimes I think about this, right? I have the same objection you might have, right? But then I think,
No, I'm not
let's say
objecting.
let's say I observe Earth, right?
Uh-huh.
And I look at Earth with this, in particular patch of the sky, and I see ocean, right? Am I going to infer that the entire surface of the Earth is covered with oceans? I don't know. So I need more data points, right? So I think that's a philosophy.
I know, but I guess it's a great question to ask. So the lens part, the part of the galaxy, or the part of the images that Hubble are going to take that has the lens field in it,
Yes.
will be for detecting those first galaxies, or at least pushing the limits of the faintest galaxies
Yes.
Hubble can see.
Yes.
The other field is just one of these. Is the deep universe the same
Yes.
everywhere we go?
Yes.
And we're doing this 6 different clusters, so we'll have 12. Can you really call the ones that are on the lensed images though? You can't call those deep fields, really, can you?
Well,
They're pretty deep, actually.
we're calling them frontier fields, but they're
Yeah.
very deep.
Yeah.
Yes.
Okay. All right.
They're,
Sure.
they're the deepest ever observations of clusters, and
Okay.
basically, it's second only to the ultra deep field in
Mhm.
depth.
Yeah. So that's pretty. This is like, I think, the most important thing Hubble is doing right now. So tell us, you're going to be doing this for a long time.
Yes.
How
yeah,
long?
we just started. Well, it's a 3-year campaign.
3
So
years.
we'll be doing two clusters a year over the next 3 years.
And you guys got an insane number of orbits, right?
Yes.
To do this with. How many
Yes.
orbits you get?
Well, each cluster will have 140 orbits
Okay.
times 6, so that adds up to 840 orbits. Yeah.
And just as a comparison, the Hubble Deep Field was 150.
Yes.
Right?
Yeah.
So
Yeah.
So we're gonna.
there, right? It's
Yeah.
the same depth, basically,
Yeah.
you're getting.
And so just so you don't, just in case you were wondering, the unit of time in Hubble is an orbit. That's the amount of time it takes to go around the Earth. And so you're allocated, when you're given Hubble time, you're given that time in orbits, usually.
So
About 90 minutes.
Yeah,
Yes.
140. Well, yeah, 140 orbits works out to less than 90 minutes in actual exposure time, though.
Right.
Right. So
That's right.
so you've been doing this over 3 years. We're going to, and recently, and with the reason for today, the big news today is you're finished with one, or you got the first epic done on
We've
one of them,
got
right?
the first set of data on our first cluster.
The first set. So explain that first set of data.
Okay, so because we're doing this thing where we turn on 2 cameras, right? We have to turn on 2 cameras and then come back, right? So we've gotten very deep infrared images of our first cluster, though these infrared images are, giving us the deepest view yet of the universe. But we're coming back. We're coming back in May.
Right.
And we're switching the cameras and getting even more data. And that additional data is going to tell us a lot about the distances of the galaxies that we see in those images.
How's that? So now you're going to rotate. So that basically the Hubble, what was taking the lensed galaxy, the camera that was taking the lensed the galaxy cluster, the lens cluster,
Yes.
is now taking the parallel field.
Yes,
Correct.
it basically does a 180 flip.
Right.
Yeah.
And the other camera is looking at the
The
lens
other
cluster, and that tells us distance.
Yeah, so
How?
So the universe is expanding, right?
That's what I've heard. Yes.
And
Yeah.
galaxies that are further away from us are moving away from us faster and faster. So that actually causes something that's equivalent to the Doppler effect in the colors of those galaxies. These galaxies appear redder. So the further away it is from us, the redder it appears. And so by using many different filters, different colors, basically with Hubble, we can pick out those reddest galaxies, and those are the things that we think are the most distant objects.
Now there's a name for that.
Yes,
What's
it's
it called?
called-
So you put a
Cheaply, let's
filter.
put it that way.
That's right. You put a filter in Hubble. It's got a certain wavelength in it. You know it's red, and if the image is bright in that filter and not so bright in some of the other filters that you've imaged with it, you can kind of get a rough idea of how far away it is. How accurate is that?
It's pretty accurate, yeah.
To within, I mean, I don't know how you meant to within what.
So it depends on how many
Depends on the number of
filters you
filters you
have and
have,
so
and
forth.
Okay.
But people are getting to 5% accuracy.
Yeah.
Now, what's the other way of finding out how far away something is?
The hard way.
You have a hard way. You have a lot of time. You have to take a spectrum, right?
Yes.
Right.
So
High
you have to
resolution
take
spectrum.
many hours with something like the Keck telescope or the T telescope and look for spectral features in the galaxy that are high resolution. So maybe an emission line. So
that's a bright spot, a bright line in the spectrum.
Line. So the
Right.
most recent, high redshift galaxy that was in the press was an announcement of the highest redshift galaxy that was confirmed by the spectroscopic technique.
Okay.
Looking for emission from hydrogen.
Is that typically more accurate?
It's definitely more accurate, but it's much harder.
Right.
And it's actually very hard at the early universe because we actually don't see a lot of emission from hydrogen in those first galaxies.
So there's not a lot of features to actually see and mark on the spectrum itself.
I mean, you can think of, this is perhaps a crude way to say, but you can think of the spectrum as a high resolution and the fundamental redshift as an approximately for galaxies. So you infer what the spectrum of the galaxy is, and then you figure out what the distance is. Right?
That makes sense.
So the
Sure.
spectrum, you have extremely high resolution, but as Jennifer said, it's extremely costly, right?
Is there a relationship? Now, how much longer, if you tried to do that with, not that you could do it with frontier fields, but if you tried to take a spectrum of one of these faint galaxies, the lensed galaxies using a spectroscope.
What's a mag? 29?
Well, you cannot do it for the depth
On the
of
ground.
it.
That's right.
On the
You
ground.
can't. That's what I was trying to get at.
Yes.
Okay.
You can only pick out the brighter. You can
Right,
go
brighter. Yeah.
But there are galaxies in these images that are probably 20 or 50 times fainter than anything that tech could really detect.
Okay. All right.
And to the expector, right?
And they used it in the original Hubble Deep Field too.
Exactly.
Yeah.
Exactly.
Yeah, that was a really productive survey, Stone was. I got a lot of good data.
I know a lot about it because I did it a long time ago.
So what's Hubble looking at now? You've moved on to the next galaxy, to the next cluster,
Yes,
haven't
as
you?
we speak. It is moving on to the next frontier field.
Awesome.
Yeah.
All right. Well, which one is it?
It's Max 0416.
See, weren't you going to say that? I was.
Well, before we move to the next cluster, so
What's this one?
no, what have we learned so far?
Oh,
Yeah.
okay. All right.
Well, it's actually
What is that
very
telling us?
early days.
Yeah, I know. But
There are a lot of galaxies.
do we have any surprises so far? You think?
Surprises. I don't know. I think these images go really deep. But the reason why people haven't done this before is looking at a cluster is actually a lot harder work than these blank fields of the cluster itself. Right?
Understanding what the shape of the lens is.
Yes.
That's
How much is it magnifying these?
Now you're getting to a good. Yeah.
Right.
Okay. I was going to get to
So
that.
that's hard. And then we have these pesky, annoying cluster galaxies in the way. Which if you want to study the distant universe, you don't care about them. I mean, you want their gravity to make things look brighter,
without
but you
them,
don't really want the light.
Yeah.
So.
I see. Yeah, I guess they would be in the way, wouldn't they?
Yeah, so I think so. So job number one is to figure out the mass distribution, basically. How much mass there is in there for you to reconstruct what the lens is doing, because all the lensed galaxies you see, you have to be able to understand exactly how the lenses actually work.
That's right. In order to understand what's being lensed, you got to know what the lens is.
What the lenses are based on the observations, which is actually very interesting because they're very, very similar. They look qualitatively very similar, right? But they differ. So it's a growing field of people trying to understand exactly what the distribution. It's very fascinating, actually. It's very, very interesting.
So how'd you pick which ones were which models to use? I mean,
which models to use?
I mean, it's on some level it strikes me as it must be a little bit of a guesswork involved, right?
There's guesswork involved, yeah. So people use a combination of techniques to figure out how much mass is in these clusters and where that mass is, and that's what gives you the magnification. You can use Hubble images. So if you see the lens galaxies, the positions of those lens galaxies, put constraints on the models.
Okay.
And so
you know what it is. You know what the model is.
Yes.
Or what the lens is.
You can make a prediction. It's like, okay, if I see this galaxy here, I should see multiple images of that galaxy.
Okay.
So if you see a counter image here and here, then that puts a very good constraint on that model.
Right. To some extent, it's kind of an optimization problem. You lay down your guesswork for the mass distribution, you compare it with reality, and then you keep going back and forth, and you optimize and you try to, find again all the multiple images, all the the stretched galaxies that you see.
Yeah,
and it's
stuff in there too, causing all kind of mischief, right? Yeah. So you kind of have an idea of what the model should be like. You have predictions, and you're comparing them with observations. You go, that model's doing a pretty good job, but you have more than one. You have six, right?
Six,
why you need so many?
That's a good question. Well,
they can't all be right, can they?
Same reason we talked about before. We need more data points. Come on.
Yeah, but you want the right data points. You want to do the right thing.
Well, there are different techniques, right? For the majority of the image, the models agree pretty well.
Okay.
But it's where things get interesting that things sometimes disagree, and that's actually what we want to know the best. Right?
Oh, okay. So there's these parts where these two models aren't saying the same thing, but they're mostly right.
They're mostly right on average, but the regions where there's the highest magnification, different modelers get different estimates.
Oh, really? So the parts where you're getting some like really big lensing going on.
Yeah.
The model.
So there's there is a shallow survey of clusters called CLASH, right? One of the things CLASH has done.
Cluster lensing and what's the S? Oh, shoot. Survey using Hubble.
Ask Dan.
Yeah.
So one of the things they've done is look for supernovae. So supernovae, type 1 supernovae, are standard candles.
That's right.
If you know you found that one, you know what its distance. You know what its intrinsic brightness is.
That's right.
And you can measure its redshift independent of that. So that's used for cosmology, Nobel Prize, all of this.
That's
stuff,
right.
So the CLASH team and Steve Rodney found 3 lens supernova in the CLASH survey, and those type 1A supernova looked. So it was lens, and you can get a completely model-independent estimation of that magnification, and you can compare it to the model, and it did really quite well.
Oh, awesome! That's great. That's exciting. Well, God bless Type 1A super. I mean, come on, they help us more about the universe. They are. They just keep making us know more. They just help us with the universe every time we turn around. Okay, so we have models. We've got. It's okay. You want to join us? We got people walking around while we do all this, so it's all over the place. But so, what is the most? What are you most excited?
Something completely unexpected. So it's the things that we haven't thought about yet that we might find.
So far things are going as I expect. They're going pretty much the way you hope they are, but surprises are in the.
I think there are surprises in there, and really, people have only had their hands on the data for a few weeks.
That's true. We only started in October,
and we don't. Yes, we started in October, but the final beautiful images were not produced until just before Christmas.
Right.
And we only have like half the data, right? We're going to get a lot more data. We're going to get Steve's first set of data, but I think the real, groundbreaking discoveries may happen later.
As the project progresses on. So let's talk a little bit about this. Is not just Hubble, right? We're not just using the Hubble Space Telescope in this endeavor. You want to talk about who else might be involved?
Sure. So Hubble is spending a lot of time, mostly director's discretionary time, on this project. But Spitzer Space Telescope, which is an infrared space telescope,
that's right,
agreed to coordinate with us and is also devoting something like 1,000 hours to look at these clusters.
Wow.
And go very deep. And this is really important because if you want
to explain, that's really that works in a wavelength range different from Hubble.
That's right.
Much lower.
Down. It's redder. Yes.
Longer wavelengths.
Longer wavelengths.
Right.
Yeah. And so that's useful for this photometric redshift that we talked about. And then the other thing it's useful for is at greater distances, higher redshifts. Spitzer is what captures the light from the bulk of the stars in those galaxies. So Hubble is really looking at the rest frame ultraviolet light that's been red shifted, right?
Sure.
And that probes the star formation, the young stars.
I'd love to get into that at some point. That's a fascinating topic. But
if you really want to see all the stars, you got to go redder.
Right. So because of where they are and how far away they are, Spitzer does a better job of showing us the stars inside those galaxies.
With the wavelength it's looking at. Yeah.
And so you compare those clusters.
Matching to the Spitzer data.
Okay.
In photometry.
All right. So you're comparing what you get with theirs. And anybody else?
Chandra is starting to X-ray additional imaging.
What's so great about X-rays here in the faraway galaxies?
Well, there are two things, right? So Chandra is good at detecting. Actually, they always study clusters, and they already have some data on this. So that's that X-ray hot gas that lives in the clusters, and that is a good tracer of the mass of the cluster, which helps put its constraints on our model.
How bright it is in X-rays is linked to the mass of the galaxy?
Of the whole cluster.
Of the entire cluster.
Stars stripping out, gas stripping out, and that gas gets heated by the cluster.
And so the combined brightness of all of those galaxies in the cluster in X-rays tells you how far the cluster is.
No, it's the gas.
It's not the galaxies.
It's not the galaxies.
gas.
Just the gas in between the
Just all
galaxies.
gas.
Yes,
Right.
yeah.
That tells you basically, you're looking at what is the mass that bounds that gas, in this cluster, and then as you said, it's because of friction stripping, tidal stripping, and everything else, these gas get heated.
Okay.
So it gets heated to temperatures that are typical of 10 to 6 degrees or so. They're typical of X-rays, right?
Yeah.
So that's why Chandra
Millions
is
of
perfect.
degrees.
Millions of degrees.
Yeah, 10 to the 6.
Sorry, millions.
So the other thing that Chandra is good at finding is black holes.
Yes.
So black holes that are feeding gas and actually heating the gas.
And that's because black holes have jets
Yes.
that come out when the
and
when it's
they
heated.
have these little discs of gas that fall into them.
Right.
Yeah.
And so we'll look at the hot X-ray gas in the cluster, but we'll also look for black holes behind the cluster that live in these distant galaxies.
Okay,
Wow,
cool.
that's my model. That's great.
So what's next, Jennifer? What do we got to look forward to coming down the pike?
Well, right now Hubble's observing the Frontier Fields Cluster number 2.
Number 2, the Max Club.
In May, we're coming back to ABEL 2744, and then we come back to Max
These
0416.
things are going to be household names, but
Yeah.
soon.
And so,
We should get out of the way so people can see this thing. I guess.
and so by the end, by next fall, we'll have the complete data set on the first 2 frontier fields, and then we'll be moving on to the next ones. So.
Okay, so I've been waiting. I've known about some things before this thing happened. So now going forward, can I start letting people know as things come out?
Yeah.
Oh, awesome.
Yeah,
Because it's hard for me to get the public engaged.
Yeah.
So I want to point people to this image. Where can people see it? And things like that. This is, we just did a press release on the Hubble site, right?
Yes.
So if you go to hubblesite.org, go to our press release page, it'll be the first press release up. It came out at 2 o'clock today?
2 o'clock.
Right. And Jennifer did a press conference with AAS just before she came here. That should be archived on the AAS website for the convention. They have a space there where all of the press releases, they're embargoed until the press release is over. And when it's over, then they make it. And Frank Summers, I'm going to try and get him soon. He made a sort of a trailer video.
He made an awesome video.
That is awesome. He really did. And you can get that also, I think, on the press release. I haven't looked at the press release. I haven't had time.
If it's not there, we'll get it up soon.
Yeah. So you'll be able to see, and I'll talk with Frank in just a little bit about this as well, because he made a really awesome trailer for it, and Brandon as well. So, Jennifer,
thank
you. This is
You're
fun.
welcome.
Thank you very much.
Thanks.
That's Jennifer Lotz, the PI for Frontier Fields. So
Yes.
thank you.
Thank you.
Thank you very much.
Bend space and time around. So those most massive objects are clusters of galaxies. And this bending of space actually means that light traveling by the cluster gets bent, much in the way that light moving through a telescope gets bent. And so gravitational lensing means that the galaxies that are behind the cluster appear magnified, they're stretched out, they're brighter, they look bigger than they would otherwise. So these clusters are acting like natural telescopes.
So we've talked to some of the members of the Frontier Fields team before, so you know what the project is. We've already introduced it a little bit, but let's give a review. With me here is Dr. Jennifer Lotz. She is the principal investigator for the Frontier Fields project survey. Jennifer, why don't you tell us a little bit about what Frontier Fields is and what you're hoping to accomplish?
Sure. So the Frontier Fields is an ambitious 3-year campaign to try to peer deeper into the universe than we have ever before. So you may have heard of the ultra deep field, right?
Yes.
So,
yes.
I don't know, about 1.5 years ago, the director of the Hubble Space Telescope asked a group of scientists whether it was possible to top the ultra deep field. Right.
That's a tall order.
Yes,
That's
it
super,
is.
that's a very
because
tall
we've
order, yeah.
spent hundreds and hundreds of hours looking at one little patch of the sky, and we've learned a tremendous amount from that field. But we wanted to know, was there more to learn with Hubble about the early universe in the years, between now and the launch of duty. And so this group of astronomers said yes, but you got to use a trick, and that trick is employing Einstein's theory of general relativity to use something called gravitational lensing. So they're the most massive objects in the universe. Actually,
So galaxies that would otherwise be out of Hubble's detection range come into Hubble's capabilities.
Exactly. So we've got our natural telescope and then Hubble. So it's kind of like two telescopes.
Yeah, it's like
right?
putting two pair of binoculars right up.
So I was actually going to say, I love this. I love this frontier fields because basically you're told you have a telescope, you're taken it to its limits,
Yes.
and you reach the limits,
Yep.
and you're told you cannot go past this. It was like, whatever, we can use nature, to help us really to go further.